Hey, how's it, everyone? I wanted to do a quick series or maybe a few sessions of just talking about Web3 from a developer perspective. So Web3 has become popular again, I suppose, in the last 6 months. And maybe it's already starting to die down again. And I suppose that's the function of the cryptocurrency world is that things get hyped up and then they sort of die down, then they hype up again. And that's pretty normal. Um, but I've spent quite a fair amount of time with Ethereum a couple of years ago and playing with smart contracts and the Solidity language and try to understand that stuff. I think more recently, what's quite interesting is we see this emergence of what you would call Generation 3 blockchains. So, for example, Cardano, Solana, Near protocol are very good examples of these third generation blockchains. So, if you consider that Ethereum is a second generation blockchain, it was really the first blockchain supposed to introduce the idea of smart contracts or Web3. Um, and although Ethereum's been around for a long time, it's much slower to evolve and add new features because, of course, it's a running blockchain. So you're seeing these third generation blockchains coming up without any baggage, and so they can do things kind of perfectly from from the beginning, or at least solve some of the core problems that are difficult to solve once a blockchain is running, coming out. And it's very interesting to see some of those things coming out. And so it's definitely worth understanding Web3 in a bit more detail. So I thought for this for today, what we could look at is maybe from an agenda perspective. I thought like let's get into technology quite quickly, but I thought it probably makes sense to understand like why Web3. So why does Web3 exist, or potentially like what problem is it solving? Um, is it solving, or what problem is it trying to solve, or what issue is there in Web 2 that requires us to rethink like the internet, right? Or the web part of the internet, I suppose. That's quite interesting. Then definitely worth understanding the architecture um, of Web3, or certainly how you should think about architecting things for Web3, and probably interesting versus a sort of cloud um, architecture. So when we think of building web applications today on the current internet, um, we would probably quite quickly think about, okay, we've got to build some sort of web front end or mobile front end, and it's probably going to talk through internet protocols, maybe HTTP or WebSockets to some kind of service somewhere. And maybe we want to build an API for that service or whatever it is. And we probably end up deploying that onto like a cloud infrastructure. I mean, of course, we could put it onto actual servers racked and stacked, but today probably not. We would certainly spin that up on an AWS or Azure or GCP or whatever it is, or Heroku or anything. But generally, a web application today is this combination of a client front end, the kind of thing that is going to run in people's browsers or on their phone, some kind of protocol that is talking to some sort of back end, and it's a typical sort of web architecture, right? Of course, you might have storage and data and other services, maybe data things and S3 buckets and stuff like that, of course. But I put that in sort of the services side of it. So we've got a client, some protocol, and a server. That changes fundamentally with Web3. And so it's definitely worth understanding it from an architecture and kind of how it works versus what we would expect from a cloud architecture. And then I thought it would be really cool to build an example. So let's actually build an example smart contract that's worth doing. So let's get the actual tool chain up and running. Let's build an actual smart contract that we can interact with. And then we can we'll deploy it. We'll deploy it onto, I think we're going to use the Ethereum blockchain today just because it's the kind of most mature, and it is definitely one worth learning. I think the others also worth learning, of course, but I think but Ethereum will give you a good grounding as to like the basics of this stuff. I think as you move into the other blockchains, they've got, or the other generation blockchains, they've got different properties that they bring, to Web3, but they're all fundamentally of the same architecture. Maybe there's certain small details that are different. So we'll deploy the smart contract, and then we'll build like a web app. We'll actually build a web app that interacts with that smart contract. And this is often called like a dApp, sometimes capitalized like that with a D, or a dApp, maybe you call it a dApp, and the D stands for distributed. So it's a distributed app. So a web app talks to a Web 2 type of architecture, whereas a dApp talks to a Web 3 type architecture. So we should probably start using the word dApp for most of our web things that we talk about. Okay, so why Web3 and what problem is it solving? Okay, so if we think about the internet in its current form today, really what the internet gives us is this really cool idea that we can sort of have these nodes all over the internet, and nodes can be client nodes or server nodes or whatever it is. It doesn't really matter from an internet perspective. You've kind of got this ability to put connected things onto this large uh, network, right? And you can address them. So if you think of TCP/IP, you can think that IP addresses are these addressable nodes on the internet. Some of those could be clients, some could be servers. It doesn't really matter. From an internet perspective, it doesn't really matter whether you're a client or a server. You just got an internet address, and then through that internet address, we can post um, data to other nodes. And of course, it's a bit more complicated with things like port numbers and all that kind of stuff. But fundamentally, what you have on the internet is this network of nodes that are addressable, and we can move kind of data between them in this sort of very dynamically connected thing. And this is awesome. And so from this low level idea, there's become like very strong, good emergent patterns, I suppose. So, for example, client server or HD or the web itself with browsers and servers has emerged from and has it overlaid itself, I suppose, onto this network where we can kind of separate the world into clients and services, maybe there's servers, I don't know, clients and services can talk to other services. But we can even break this rule though, where services can talk to clients. I mean, this is absolutely possible with things like WebSockets or even push notifications. Is one method of doing that, and that all fundamentally uses this highly connected internet thing that we call the web. And so this is brilliant for moving data for moving data around. So this is the internet of data, or maybe the internet of content, or whatever. So we can move things between stuff. Um, However, one of the difficulties is when we start to move up into this world of, like, I suppose you could call it like of e-commerce, where now people would like to start doing financial transactions across this internet, and that is where we end up struggling. Um, and so let's actually draw a quick diagram of like an example where Tom buys something from Amazon. Yeah, that makes sense. So we may have Amazon over here, and we have Tom over here on this highly connected internet. And while Tom, I'm trying to buy a book or something like that, I add it to my cart and I click checkout. It's like, I want to buy this book. I want to buy this, and I tell that to Amazon. And this is using the internet of data. Amazon goes, cool, and we'd love to sell this to you. However, and now we need to take money from you. So what then has to happen, and I'm going to like super summarize, is Amazon will tell Tom, okay, could you go and just chat to our payment provider? Maybe it's PayPal. It probably isn't PayPal, but I'm going to use PayPal as an example. Go talk to PayPal, um, and PayPal will go and take that money from you. Cool. So then Tom goes to PayPal, says, cool, I'd like to pay for this book that Amazon says I should speak to you. PayPal then says, cool, will you give us your credit card details? And so in comes so then I provide PayPal with my credit card details. Then I'm going to change my color. Then what happens in the background? PayPal takes my credit card details, posts them off to maybe someone like Visa or MasterCard, depending on what card I'm using. Visa and then MasterCard then goes and talks probably to my bank, maybe, or somebody. And there's many people along this chain here, potentially many along that chain as well. Um, but fundamentally, the bank has to say, yes, this credit card is valid, or there's funds in the account, or whatever it is. They have to authorize the transaction. That then bubbles back up to Visa. Visa then says, cool, the transaction is completed. PayPal, it goes back to PayPal. PayPal says, yes, thank you. We can now conclude the order that Amazon told us about. And then potentially in the background, once that happens, PayPal then maybe messages Amazon to say like, hey, things are okay here, like for this order, that is okay. PayPal then replies back to Tom to say everything is okay. Tom then comes back into Amazon to say, I think everything is okay. And then Amazon finally says, yes, everything is okay. So, and at that point, my order is placed. Um, but what you can see with this is that although we've got this super highly connected internet where we can move stuff around, we can still see like a stark separation of two kind of networks here. We've got this one that we call the data internet, but then we've also got like we've ended up separating and creating like this like payments internet, that's called payments network right in the background. And why is this? Why has Tom not just gone and passed, his money directly to Amazon? And it's because of course you can't. And so when you're moving money between parties, there's this fundamental requirement for trust that Amazon needs to trust PayPal, PayPal needs to trust Visa, Visa needs to trust the bank. Um, in order to actually allocate those funds. So when Visa says to the bank, hey, Tom is spending $10 with Amazon, Visa needs to 100% trust that the bank is going to take that money out of the account or put it on hold or whatever it is, do something important with it. Visa can't really check it directly. It has no insight into the bank accounts of the bank's clients. It can't actually physically see, nor can it physically move the cash. So it has to rely on the fact that it has a trust relationship, that Visa and the bank have got a high degree of trust between them. The same is true of PayPal to Visa. When Visa says to PayPal, yes, this transaction is authorized, PayPal is taking on the liability of that order, of those funds. It's going to approve an order of a book based on the promise that it's going to receive $10 into its bank account sometime into the future, which will then pass on to Amazon's bank account sometime in the future. And if it doesn't trust those parties, it wouldn't approve that transaction, right? So we have this very high degree of trust requirement on this side of the world, which we really don't have a good mechanism for on this side of the world. So we know this of the traditional internet that you can't between two nodes, between this node and this node here. It is very difficult to have any level of trust. Um, and especially when it comes to something like money. And why is that? So when we think of money, when we think of cash, often I think of this word, bearer instrument. So the word bearer instrument, although it sounds scary, is not that scary. Bearer is very important to this thing. Bearer means whoever holds it owns it. So whoever is holding the cash money has the cash money. And if they want to buy something, they just physically have to give that cash money to the other person, and the ownership of that cash money has changed hands. So the flow of value of cash, if this is a sort of a $1 bill or €1 bill, whoever holds it really owns it, right? That's the physical constraint of bearer instruments. And that works really well in the physical world. It doesn't work in the digital world because digital stuff, we know there's no concept of bearer, of like who owns the data. Because data can be copied, it can be transferred, it can be duplicated, replicated, it can be modified. Like data is a very non non like a non transferable idea, right? So it is a terrible, it is very difficult to build a bearer instrument on top of anything electronic. And so because of this, we have we have this breakdown or this separation of these two networks. The one is the really the services network or the data network, and one is the payment and trust one. And the idea of Web3 fundamentally is that we're trying to solve this problem, that we would like to bring together um, the content as well as the value. So being able to move money around onto the same set of infrastructure. So that means that in our previous example where we had Tom buying a book from Amazon, that we could really do this. When Tom places his order, we could actually have him send the money directly over the channel and have Amazon directly deliver the book or whatever it was that I purchased back over the same internet channel. And really, the fundamental thing is that we're trying to bring these two things together into what we would call a smart contract. So really, it's the instead of Tom trusting Amazon and Amazon trusting Tom, what they can do is they can form um, a smart contract between them where they can agree that if Tom puts the money in for the book, Amazon will put the book in, and as long as the book is in the contract, the money will swap. The money will flow to Amazon, and the book will flow to Tom. Really, that's the idea of the smart contract. And so it's really what we're trying to do is we're trying to bring the world of commerce into and make it a first class citizen in the regular old internet of data. So what does the architecture look like? Well, we know that these things are based on a blockchain. And so I suppose we could have the blockchain down at the bottom. And so why do we need a blockchain? So really the most important thing to solve is the double spending problem. So when it's this idea of duplication, so it's really to try and get back to that bearer instrument. Whoever holds this thing has that value. And so the idea of a blockchain is that you have some place in storage somewhere, which always holds the latest set of accounts. So who owns what values or what amounts of currency are in which wallets. And the reason why it's really a blockchain and that there are blocks in this chain. So maybe it moves this way. So we have kind of the starting or the genesis block starts over there, and each of these blocks are numbered and they sequentially increase over time. New blocks are only ever added here to the front of the blockchain or to the head of the blockchain. We never go back and modify anything in these things here. You cannot. In fact, you have no ability to go back and change the values of things inside those blocks. Once a block is created and attached to the head of the blockchain, it is cemented. And so once you have something like that, you have the structure where you're just adding new things onto the top. And those new things added onto the top can have effect on things that have happened in the past. Like, for example, in the past, if I received 10 Rand into my bank account, and in the new block, I have sent 10 Rand out of my account, by analyzing those blocks in order, I can see, oh yes, Tom received 10 Rand, and then later on he sent 10 Rand. So what is his current balance as of this latest block? It is now 0, plus 10, minus 10. So you can imagine the blockchain is really this recording of like all of the mathematics of transactions over time. Just add 10 minus 10 plus 100 minus 1,000, whatever, and over time that gives you an idea of which wallets, which accounts in that blockchain have got what values associated with them, and those are obviously always changing into the future. So really fundamentally you have this thing at the bottom, which is this blockchain, which is keeping a recording of everyone's current balance. And this does solve the double spending problem if we can say strongly that there is only one of these things in the world, there is only one instance of this blockchain. And if everyone subscribes to that, if everyone believes that it is the one blockchain, then actually we can start to use that as our mechanism for sending value to each other, if that makes sense. So in the Ethereum example, in the Ethereum blockchain, it still relies on something called proof of work. So proof of work is, let me write it up here, proof of work. Proof of work relies on the fact that um, creation of the next block is done through the demonstration of very high amounts of computational power and and a network of those. So it comes down to a set of nodes in the Ethereum network, all coming out with really the same block at the end of the day, and then having consent over that block. So as long as 51% of the network all agrees what the next block should be, this one over here, it will be accepted by the network. So when we move on to the next block, we will look back and we'll say, okay, we created a block. We can see that 90% of the network or more than 51% of the network of nodes agreed that this is what the block should look like, then that is the block. And when we start building the next block, we will build it on top of the most highly accepted prior block, if that makes sense. And so the idea of proof of work um, and really, the fundamental idea is that we're trying to avoid manipulation of this blockchain. What we want is bad actors. We don't want bad actors in the creation of blocks. We want generally the right block to be created, and that way we can build trust. And so, how does that work with, well, certainly with Bitcoin and with Ethereum today still, we have this concept of proof of work. And so, um, really what it's trying to say is that in order to modify a block, you would have to have at least as much computational power as more than 50% of the size of the network as it stands today. And so the idea of that is the economics of it just don't make sense. So in order to change a block or to change the prior block, I would have to create that block. I would also have to put so much computation. I'd have to prove mathematical problems inside that block, which would require me having the computational power of the size of more than 50% of the current Ethereum network today. And when you look at the current rate of hashing of the Ethereum network today, it's very, very high. So and so there's thousands of nodes all running, GPUs or ASIC miners or whatever they are, these very high computation hashing per second type of devices, which are trying to solve mathematical problems. So the idea of modifying blocks is based on the fact that the network can demonstrate a certain amount of computational power went into each block, and so therefore it's very hard to modify that block. And then as blocks get attached onto the end, as the next block gets created here, it then starts to compound the computational power of prior blocks. So as the network moves forward over time, blocks, historical blocks, these ones, and these ones, become like exponentially more and more and more difficult to modify because of the concept of the layering of computational power over time. So in order to modify this block down here, if I wanted to go and change something in this block here, I would go and change it. I'd have to resolve the solutions here, but then I would also have to go and recalculate all of the blocks that have moved on into the future on top of this. And the idea of that is that should be so computationally be difficult to do that it would become economically infeasible for me to do it. So that's cool. That's how the Ethereum network works, and that's the fundamental of proof of work. There is an alternative idea, or maybe a nicer, a newer idea, which is proof of stake. Um, and it is worth understanding the difference because so proof of work relies on the fact that I have access to a lot of computational power, and so it makes it very difficult and very infeasible to recalculate blocks in the past and then forward through into the future. I'd have to defeat the entire power of the Ethereum network in order to do that. Um, what proof of stake says is that instead of doing that, instead of computational power, we could use the idea that you put something up at stake. So when you've got all these nodes on the network, maybe they look like, maybe we've got sort of 5 nodes and they're all collaborating to create the next block like that. They all, so with proof of stake, and certainly on Ethereum, maybe I should say rather maybe with something like Cardano, which is really a proof of stake network. The way it works is these nodes that are calculating the next block, they put up actual value at stake. So they really lock actual hard currency into their block producing. So they load up actual hard currency, and it's not dollars, but it's ADA in the Cardano network. But ADA is a full-on cryptocurrency, and it has a dollar value associated with each ADA. So each block producing node puts at risk, I suppose, some amount of ADA. And they say, hey, this node may have like 1 million ADA um, at stake. This node may have 500,000 ADA at stake. This node may have 2 million ADA at stake, etc. And then what the network does is it randomly chooses a node to produce the next block. So say, for example, this node here, node 3, gets selected to create the next block. It creates the next block. It then publishes it to all of the other nodes to validate. And and then all of the nodes then go through a voting process of saying, is that the correct block? So what they do is they themselves then calculate that same block and they compare it to the block that node 3 created. And they say, yes, we're happy that this is the correct block. And they all go through a voting process. If it turns out that more than 50% of the network um, votes for that block, then that block is accepted and it is attached to the head of the blockchain. If it turns out that that block is not accepted, because either it was false, there was a bug in the code or something, or it could be that there was a malicious transaction inserted, then that node there is some mechanism for that node to lose some of its stake. And so what that means is, using the theory, like the idea of game theory, is that generally you're going to find it makes better economic sense to create a valid block because you will not then lose your stake, if that makes sense. So that's one of the defense mechanisms. Of course, by creating blocks, there is also something to be earned by that node. That node ends up benefiting if he creates the right block and it is correctly and is accepted by the network. He can earn a fee off of the creation of that block, which then debits straight into his own ADA account. So the idea of proof of stake is that you put something at risk to participate in the network. If you are found to be a malicious actor, you stand to lose some of whatever you put at risk. If you are a good participant, you stand to earn some benefit on the side. And so the idea of that, whether you believe it or not, is in terms of game theory, it tends that a network with with that sort of basis tends to do the right thing. So it tends to be people tend to be honest and trustworthy in that environment, and that it automatically sort of pushes bad actors out of the network. In order for someone to attack this network, they would have to introduce a large percentage of bad actors in order to also validate incorrectly. And then, of course, even if they end up defeating it and they end up creating a bad block and they steal all the account balance or whatever it is, um, they end up directly affecting the value of ADA as well. So if a bad actor had to come in and steal all of the ADA, you would find that the value of ADA ends up decreasing, right? Nobody wants to buy stolen ADA, and so then it also naturally brings, has an economic force on why you would attack it. So, I think in the early stages of a proof of stake network is where it is its most vulnerable. So when it's in the early days and there's very few nodes and there's few participants, that's potentially where one of these networks is easy to attack. But once one of these networks gets beyond a sort of certain critical threshold, it becomes very difficult to attack it. And as long as those stakes continue to be left in those nodes, and more nodes are added with more and more stake, it becomes over time it becomes a very difficult network to attack. Potentially even more difficult to attack than a proof of work network. And of course, you have the side effect that proof of stake requires very little computational power. And so you have all the you don't end up buying up all of the GPUs on the planet or burning fossil fuels in order to create and mine Bitcoin. You just end up with just having value locked into a contract and very low computational requirements. Really, just a set of connected nodes that every now and then create a block. Actually, not a big deal. So, how do miners earn fees? Let's redraw it. So that involves people actually submitting transactions. If this is our blockchain here, and with the next block being calculated down there, so it's moving in this kind of direction, and there's blocks like that. We've got our nodes calculating the next block. So these are the guys. One of them will end up solving the next block and will create that block there. Where do they get their transactions from? So they have something called the mempool, and the mempool I think is a Bitcoin. It was coined with Bitcoin, but I think Ethereum also calls it the mempool. I think all of the blockchains call it a mempool. The mempool is this shared piece of memory that is not yet part of the blockchain, but it's kind of the candidates of transactions um, that are being mined for the next block. So effectively, it contains the list of possible transactions that could make it into the block. And the mempool is the thing really that clients end up communicating with. So so me sitting here, when I want to submit a transaction into the network, I end up somehow through some mechanism end up writing to the mempool, which is like the staging area for transactions. I obviously can't write straight to the blockchain. I write it into this thing, which then will be mined by miners, which will then make it into the blockchain. And when I write that transaction in, um, like that, I can attach a little bit of value to it again. And here's another sort of interesting mechanism that when it gets written in here, um, when my transaction makes its way into the mempool, it is attached to a little sort of bribe associated with it, some sort of incentive for miners to mine my transaction. And so the mempool is yet once again driven by incentive. So when a miner is producing the next block, all he does simply from an algorithm perspective is he reads the mempool, sorts them by highest value because he wants to mine the highest value transactions first. When he ends up solving the block, that ends up containing the set of transactions with the highest value um, things from the mempool, that then gets cemented into the block down there, and the miner ends up earning sort of the accumulation of all of those fees. So he ends up getting all the fees of all of these things added to his own account as the reward for mining that block. So you can see that through this mechanism, we have a sort of a front end to the blockchain through the mempool. And then we also have a mechanism through that attaching of that incentive fee, a way of prioritizing certain transactions over other ones, because as things, these transactions are being written to all the time. And so this mempool is constantly expanding. It's constantly growing over time as more and more people submit transactions. But then it's also decreasing in size as a miner whips transactions out of it and they get cemented into a block. So the mempool shortens or reduces in size for every block that gets created because transactions are effectively pulled out of it. But then it's growing because more people are adding transactions. So you have this mechanism of being able to prioritize a payment no matter what the network is doing. So the size of the network, the size of the mempool, often tells you the sort of performance of the network. So if the mempool is very large, it means there's lots of transactions in it. It means that the network is starting to fall behind. It's not able to process transactions quickly enough. So the mempool is growing and growing and growing. However, it doesn't mean that payments will be slow. It just means that people will have to pay more in order to get faster payments through it, if that makes sense. So you end up with this fee, which is dynamically calculated based on the current load on the network. So when the network is under load, things are more expensive to get payments through in the same amount of time. However, they can still cost the same. They just may take a long time to get processed. So things that that you attach a low fee to, down here, maybe I attach a very low fee. It may remain in the mempool for a long time until the mempool gets to the point in time where that fee makes its way up into the block producing half of it, if that makes sense. So in Ethereum, to bring it back to Ethereum, it's very simple. When I attach a transaction, when I submit a transaction into the Ethereum network, I often attach something called gas. And so if you know Ethereum, you would have heard that I can have Ether in my account. Ether is the cryptocurrency of Ethereum. It's the fundamental sort of currency. But then there's this concept of gas, and gas is really that little incentive that I attach to transactions that are earned by miners. So it's not one to one. Gas is not entirely earned by miners. Some of it is actually burnt and lost to the network, but there is a calculation that a miner goes through where he can calculate his fee based on the gas attached to a transaction. So it's quite a nice analogy, gas, because it feels like something I burn. So it's almost like there is a cost to perform a transaction on the Ethereum network from a client perspective, and that cost is the gas that is required to get it through the network. Some of it is earned by the miner and helps prioritize it into the mempool. Some of it is actually burned and disappears. It is literally removed from the network, creating this inflationary or deflationary type of mechanism. But I'm not going to get into too much of that kind of detail. Another thing to keep in mind is um, transactions and gas and things like that are only required when writing to the blockchain. I don't need to put a transaction into the mempool in order to read the state of it. Anybody can read the state of the Ethereum blockchain, and that costs nothing. So it costs nothing to read it, to read the current state. The only cost is when I want to make a change. So when I want to mutate the blockchain or write to the blockchain, that I need to create a transaction and attach gas. So it is only a requirement for writing that we go through this process. Reading is much simpler, and in fact, Tom can read the state of the network directly. You can always have a picture of what does the blockchain look like today. There's many different ways of doing it. One of the standard way of doing it is you run your own node. That node is yours. It will have the full state of the network in its memory, and so it doesn't cost you anything to read the state of the network. All right, so the last thing we haven't dealt with yet is how do smart contracts work? So how do we now make code work in this world? And let me redraw how we could get executable code working in this thing. So we know that in order for code to execute, well, let me just describe the mechanism. So when eventually I get a transaction into the blockchain here, and let's pretend that this is my transaction here, which is then forms part of a larger block, I can insert a bit of code into it. I could literally put some like bytecode into this transaction. That transaction can have an address. So the same way that a wallet has an address. So when Tom has got an Ethereum wallet, I have an address associated with it. I can also load code onto the blockchain, which would have an associated address with it. And it may or may not have a balance. So any address on the Ethereum network certainly has kind of got this like data portion to it. So you can load data into an address, and you can load like Ether, the actual account balance of that thing. So it may have zero. I can create a wallet with some data, but with zero balance. And effectively, that just becomes a citizen of the blockchain. Anyone can read it. They can, if they have the address, they can read the address. They can read that code or that data section, which could in turn it could be holding bytecode, which is executable inside it, right? So we have this mechanism, so we can write bytecode effectively to the blockchain. Um, Now, say we want to interact with that with that with that source code. What I could do, if I'm Tom, I could create a transaction. Here's my transaction that I'd like to submit. This obviously, as we know, goes through into the mempool. It's going to be inserted into the mempool with a fee. But my transaction might say, hey, please will you load up the function, or I should say load the contract at this address. So maybe this is address ABC, ABC, and please would you execute the function called F, like that. Then I can attach to this, like any other transaction going into the mempool, attach some sort of gas to it. Here's my gas. Got to attach gas to this thing. And maybe it does nothing else. It's not like I'm paying anyone any money or anything like that. I'm literally saying, please go and load the contract ABC and execute a function called F. But here's the gas required. That transaction makes it into the mempool right there. Miners do their usual trick where they prioritize the mempool based on the highest value. By the time my transaction gets into their memory and they're about to execute it, all they have to do is they just need to go and say, oh, okay, no problem. I already have the state of the blockchain. Go and read that ABC contract out of the blockchain. He's trying to execute this function F. I know how to interpret the bytecode here. So each of these nodes has got like a little mini interpreter of that bytecode. It can load the bytecode up. It knows how to execute this function F. It will execute it in memory. And then whatever the result is of that thing, because it may try to mutate the blockchain or whatever it is, whatever that F does, will then get written into the next block that gets created. So the outcome of whatever F did would make its way into the blockchain for that node. Does that make sense? And when he does that, he gets to calculate and eat up the gas. He earns the little fee based on that thing. Now, the interesting part here is that that fee is a little bit dynamic because that node ahead of time, nor does Tom actually ahead of time really know how much work is going to be required to execute this function F. And so typically when he attaches gas to it, he attaches sort of the idea of like a maximum amount of gas. And the actual real amount of gas that is consumed does vary based on what F did at that point in time. So when this node up here is loading up that little piece of bytecode, he starts executing, he has a way of knowing how long the execution of F took. If it took, based on like number of operations that F executed. If it did 20 operations, he may earn 20 gas. If he did 1,000 operations, he might earn 1,000 gas. And so when I submit this transaction, I kind of give this idea of a maximum amount of gas. And then the node will end up taking whatever the actual amount of gas was that was required to execute F. If he ends up burning through that amount of that maximum amount of gas, he actually just stops executing. So he ends up burning and earning that gas. When he runs out of gas, it's like, well, unfortunately, your function never executed. Well, it didn't complete its execution. It started executing, but it never completed. Unfortunately, you end up losing your gas, and the function never really completes, which means it didn't really ever make any modification to the blockchain, unfortunately. But you did probably also lose your money because the node did end up executing stuff and you took up some of his time. So that's like, so with that very simple mechanism, this is how we can execute smart contracts. So let's talk about the technology very quickly. For Ethereum, these are the things we are going to use when we build our smart contract. There's many choices, but this seems like a good stack. We are going to have a browser. So we're going to build our dApp as a browser. It's just a web the web app. So this is the usual stuff: HTML, JavaScript, CSS, etc., etc. And you can use whatever web technology you like, anything that will generate HTML, JavaScript, and CSS, so React or Angular or Elm or PureScript or anything you want. That that web application runs within a browser, as we know, but the web application itself can't interact with the Ethereum blockchain or with the mempool. And so typically the most common, certainly for Ethereum, is you install a browser extension, so something into your browser like MetaMask. So that is called, write it out, MetaMask. So MetaMask is a very common wallet slash um, Ethereum client, effectively, is what it is. Because it is correct to call it a wallet, um, but remember, it does a little bit more than just hold money in it or hold ether in it. It also allows you access onto the Ethereum network, either into the mempool if you're submitting transactions, or being able to read the state of the blockchain. So I call it the Ethereum client because not everything is related to wallet, but wallet is like primarily an important thing. So you would typically install MetaMask in as a browser extension into your browser. Then what MetaMask does is, so then your web application, when it speaks to the Ethereum network, it does it through some sort of API to MetaMask, and that is called, confusingly, the Web3.js. And it's called Web3 because I think back in 2014, when people were building this, they did see this. Web3 is a brand new architecture for the internet, and they called that client Web3. I don't know if that's the best name for it today. I would have called it maybe like the Ethereum client or something like that. But effectively use Web3.js. That is pulled into your dApp architecture, and it interacts with MetaMask through like a JavaScript API. Then, of course, MetaMask on ramps you onto either into the mempool if you're submitting transactions, or being able to read the network. So when you're reading the Ethereum network, you're generally reading the state of the blockchain through a node. When you're writing to it, you are submitting a transaction onto the mempool. That MetaMask allows you to do both. Um, and they're configurable. So you can configure in MetaMask which node you're going to use in order to. So it's actually all your transactions go through a node. Actually, when you submit a transaction, it's through a node. It's not like that onto the mempool. When you're reading the blockchain, it's also through a node. And there's a couple of managed services you can use here. There's one called Infura. There's another one called Alchemy. There's actually many managed Ethereum nodes, which will provide you your own Ethereum node in order to on-ramp onto the network. You can, of course, run your own, which would go and do that too. That can just be a bit expensive. It doesn't make sense sometimes to run a full Ethereum node if all you're doing is interacting with the blockchain and you're not taking part in mining it. So those are the technologies. You're going to install MetaMask into your browser. That'll give you access to the Ethereum network. Then if you're going to be writing your own contracts that you want to deploy, another tool, the language that you will write those contracts in is called Solidity. Solidity. Um, and that will allow you to write source code that is in the Solidity language. It will be able to compile it to that bytecode called EVM, Ethereum Virtual Machine bytecode. It's EVM bytecode, so it's the Sol-C compiler, Sol-C, which is a Solidity compiler, takes your source code, compiles it into EVM bytecode, which you can then submit into the data portion of the Ethereum blockchain. Um, and you can do that yourself. You can install the Sol-C compiler yourself. There is a cool build chain called, well, whether it's cool is up for debate, called Truffle, which I've tended to use. It's pretty good. It's not the best, but Truffle is, I think it's called Truffle Suite, maybe. You can install Truffle Suite, which kind of gives you like a JavaScript way of compiling Solidity code, deploying it, being able to migrate it, remove it, test it, that kind of stuff. So Truffle Suite is like not a bad tool chain, and it's kind of installable through npm, which is also pretty neat. So that's what we'll do in the next portion of this is we'll actually get Truffle Suite up and running. We'll write some Solidity code up here. We'll compile it to EVM. We'll deploy it to the blockchain, which is there. We'll deploy it to the blockchain. Then we'll write a dApp there, which would interact with MetaMask, which is going to then speak through a node to that code running on the blockchain, and we'll do something with it. All right, so let's get our infrastructure set up quickly. I've just created a directory somewhere. I've got Chrome open. The first thing I've done, I've already installed the MetaMask extension. There it is, but I haven't actually set it up yet. So in order to install it, I think you just Google it. I think it's just metamask.io. Let's just get there quickly. Metamask.io, click download, install MetaMask for Chrome. That takes you to the Chrome web store. Click add to Chrome. I've just done it. So there it is. And then it's this little fox face thing. You can click get started. So now you're creating a new Ethereum wallet. So I don't have one that I want to import. I want to create a new one. Maybe the same for you. Help us improve. That's fine. I agree. Create some sort of password. I'm just going to use the word password. And we create it. Some stuff happens. Yes. Yes, we do want to reveal these secret words. So these you must never show to anyone. So with these secret words, you can restore this wallet back on any machine. So this fundamentally is your password. And this is the thing that if you lift this out, if you lose all of your Ether or lose access to MetaMask or something like that, with these words here, you can restore access to that wallet from anywhere. So you don't actually have to carry anything around other than these things, and this will give you access back into your wallet. Because keeping in mind, all of your funds, your actual Ether is stored on the blockchain, which is not on your machine. It's really just your access to the blockchain is through the client. And so this is really fundamentally gives you access to your own account. So I'm going to keep these because I'm going to find that they are useful. So let me just do this code here. I'm just going to open, I'm just going to make a file here. And this is often called a mnemonic. I'm just going to store my little password in this mnemonic.txt. Obviously, don't do this with real money, but we are going to be working mostly on the test network anyway, so that's fine. It wants me to confirm them. Please select. Okay, so let's double check. Let's just do it. So it is club sudden measure silly annual avoid claw mind tourist alpha pair isolate. Confirm that. Okay, so it's happy that I've stored it somewhere. Okay, and now I've got MetaMask, and effectively it's that little guy there. You can use it through this sort of web interface, but that's not too important. And you can see that I've got 0 Ethereum. I also have an account here, which is quite cool. So if we click this thing here, you get you can have multiple accounts. So I can create a second account if I wanted to. Let's call it account 2. That's fine. And you'll see I've got a second account, and I can switch between those accounts. So when Ethereum is connected to a website, so effectively I can now just browse the internet. So for example, OpenSea is a dApp itself. It is an NFT. It's an NFT marketplace, but effectively it uses Web3 and it talks to MetaMask. So I can just go to OpenSea. You can see I'm not logged into OpenSea or anything like that. I have no account with OpenSea, but they've got a little wallet button here. And if I click that and I click MetaMask, effectively MetaMask now pops up to say, hey, OpenSea has communicated with MetaMask and it would like access to read your account data. Which accounts would you like to give it access to? This is access just really to read the values out of that account. So I'm just going to give it access to account 1. It can see address, account balance, activity, and initiate transactions. I can't actually submit them. MetaMask is still going to pop up and ask for permission, but it can initiate them, which is interesting. So now through the dApp OpenSea, I've connected my MetaMask wallet, and now OpenSea can see, oh, you've got 0 USD in your account. And you can even see it's like read my wallet account number, which is that B6A, I think. Oh, it's a different value. Why is that? Was that account 2? Oh, that was account 2, sorry. Account 1 is 38F. Yeah, 38F. So you can see OpenSea is able to view the details of that account now connected like this, and then I could go and do stuff. So I could with OpenSea, but I don't have any NFTs in this account, so that's pretty useless. But you can see MetaMask is now working, which is cool. So we want to write a smart contract. So I want to install Truffle Suite. I'm just going to Google it quickly. Truffle Suite. It's that guy. I see. Okay, Truffle Suite's got a bunch of different. That's why it's a suite, I suppose. But I'm interested in using Truffle. So I think if we go there, yeah, there's how to install it. I'm pretty sure I've done this already. Installs Truffle globally through npm. Then maybe just from a project structure perspective, what we're going to do is we're going to write a contract. So maybe this contract is the like we'll write a contract maybe that it's like a hello world contract, right? So I'm going to make a contract directory. Later on, we're going to actually build an app, like a web app, which might be the dApp. I suppose we can call that the dApp, yeah. And that will be like our whole stack. So the back end is going to be the contract, the dApp will be our front end. Okay, so Truffle's still installing. Okay, so Truffle's installed. If I can go Truffle minus help, I think. Okay, so there's many things I can do with Truffle. One of the cool ones is init. We're going to use that. So we're going to go into the contract directory. We're going to build our contract in here. So I'm going to go Truffle init. Let's see what happens. It's done some stuff. Init, scaffolder contract, scaffold test. Okay, great. What did it actually do? Okay, yeah. So Truffle has gone and scaffolded itself. Make that a little bigger. A sort of like a development environment, which is super cool. In my contract directory, I've got a Truffle config with some stuff in it. Very nice. It's got a contracts directory, a migrations directory, and a test directory. So the idea here with migrations is that you can think of smart contracts really as like data tables, I suppose. It's like database tables in some respect. And so a good idea is to like think of them in terms of migration. So when you create new versions of that contract, how are you going to keep it up to date? And so they've built a sort of migrations flow around it. So that you can see that a contract that you're referring to is the latest version, or you can upgrade. And that's great because you've got this commit log of, remember, anything you put on the blockchain is kind of there forever, but you can, of course, put down replacement versions of it over time. Of course, the older versions are still reside there. If you had to zoom back in time, you could see the old version. So it's important to take into account the flow of time. And so something like a migrations approach makes sense. We're not going to dive into that in any detail today. We're not going to use migrations probably. We're just going to build a contract. So let's actually do this. Let's go Truffle, create contract, your contract name. So maybe we just call it Hello World, right? It's the Hello World contract. We're not going to write a test for it either. Those things are for you to figure out by yourself. Okay, so if we have a look at what we've got a contract creator called Hello World. Hey, look, it's like some code. It kind of looks like C# or Java or something, but there's definitely different languages. There's definitely different keywords here going on. There's this pragma thing. I'm not going to get into tons of detail here other than give you a sort of whirlwind. I think Solidity is something you can go and learn yourself. Solidity language is a whole language specification for it. Soliditylang.org. Yeah, there's the latest version, and there's always new stuff coming out in the Solidity world. There's loads of good examples. You can get into the types that are available. There's different, of course, all the regular stuff, booleans, ints, there's bits, of course, you can add and multiply, divide stuff. But then there are interesting other types that are maybe less common. So things, for example, like there's an integer up to 256 bits. That's quite interesting. So normally when you specify the size of things in the blockchain, remember we've got to be very careful about the amount of data that we use on the blockchain, because every byte that we insert into the blockchain is going to cost us money to put there. And so often when you're building Solidity contracts, you're always very sensitive about how much data and how big operations are and stuff like that. So things like ints, for example, you can go as low as like an int 8 all the way up to an int 256, 256-bit int, which is quite interesting. And that might be a good size for something like an address. So there's like a primitive, like the word address, for example, we should be able to find it here, is a 20-byte value. So there's like a low-level type called address, which is available in Solidity, which is a 20-byte value. And that would be the size of whatever an Ethereum address is required to hold. So there's some nice low-level primitives that are very specific to Ethereum, which is super cool. All right, so for our very simple hello world program, we are going to, I mean, let's just mock it out. Actually, it's pretty simple. We're gonna have a function called greet, and effectively this is going to return sort of like hello plus something. I'm gonna go underscore because it's like a private variable or something. Let's go private string what equals. So we're going to start out with the thing we're going to greet is called world. Oh yeah, I think in Solidity these things are flipped around. So modifiers are very important in Solidity. There's the type, there's a modifier, and you can have multiple modifiers of a thing. So it could be private, but also something else. It could be like private and view, and your own modifiers even can be introduced into the language. I'm not going to get into that too much now. But that's kind of the idea. So when you create the contract the first time, the default thing we're going to greet is the world. If we call greet, we will get the greeting with that what set. But we also want to be able to kind of set that thing. So set the what maybe, and we're going to want to be able to provide like a new what, and this thing is going to go like underscore dot what equals the new what. So we're going to be able to like modify what is here. And this is the thing that will actually be stored on the blockchain. So at the moment, this is not compiling because we need to pass modifiers here. So the greet function is publicly callable. I think we also have to specify what it returns. Or do we actually? So this function return. Oh yes, this one does actually. It returns a string. So we must specify that it returns a string. That might not be good enough. Yeah, I think we also have to specify that it's a string in memory. I'm not going to get into the detail of this, but you have to be quite specific about where things are placed, whether they're in memory or whether they're stored on the chain, etc. So there's modifiers around types here at this level as well. But we're going to just return the string memory. We can ignore that. String memory here again as the new what, and this thing returns. Oh yes, we need to specify this thing's access, so it's publicly accessible. And this returns nothing, so I don't think we have to return anything here. Can we do this? Operator plus not compatible with types literal string hello and string storage ref. Okay, so we can't combine strings here. Let's just remove that fault completely, and we're just going to do that. So, okay, we've got a very simple thing. I didn't want to make it too complicated. Oh yeah, another thing I would change here is when we Google Solidity, we can see that we're at 0811. And for backwards compatibility reasons, you can specify what version of Solidity you're using. I don't know if this is a good idea, but I generally put like the current version of Solidity here because I say I'm not keen on the supporting prior versions of Solidity. I'm building it in this version, so let me specify that version. I don't know what the best practice is up there actually. Okay, so do we have any warnings here? Function state mutability can be restricted to view. Okay, that's interesting because this function here actually doesn't mutate anything. All it really is, it's fetching that value here. We can put the modifier here saying view, which then tells Solidity that, oh, this would only be a read operation. There's no write operation here. Without the view, you could look at this and go, wait a minute, does this modify the blockchain? And of course, we could choose to mutate stuff here. Because this is like an imperative language, I could mutate things and then return things. I could write and read in the same function, or read and write. By putting the word view up there, we make it very explicit that this thing does not mutate, and that means clients that call this thing know for certain that they don't need to provide any transaction a gas associated with this function called greeting is a free function, it costs nothing. The set what function providing the new what definitely is not a view function. And if I had to put view here, I think I would get an error saying that function declared as view, but this expression modifies the state and then requires non-payable the default or payable. Yeah. So the opposite of view, I suppose, is payable. So payable means that this function call, actually, no, payable takes some Ethereum. Anyway, I'll leave it off for now. It gets a bit complicated. But there is our contract. We want a contract to be non-deployment, making abstract is sufficient. Visibility is ignored. Okay, public, yeah. Maybe because this does nothing, it's not important. So because the constructor does nothing, maybe we can just whip it out. I think that's probably what it's saying. Okay, so we've got our contract. Okay, the next thing we want to do is let's see if we can compile this project, this contract. So I think there is a truffle compile. Let's just run that and see what happens. So truffle compile. Okay, we've got that migrations contract in there. Maybe we want to get rid of that. I don't love this thing. Or maybe we just leave it in. I don't know. Let's just ignore it. So it has compiled it. I don't know what it is. Let's just ignore it. But we can see that it did compile our hello world.sol. I think when the compiler runs, it creates, yeah, great. It creates a build directory with contracts again. And then it creates this JSON file, like a massive big thing. And effectively in this thing, we should even be able to get to the point where we see some bytecode being produced. Yeah, so there's a source mapper deployed. I think it is called ABI. I wonder if we can actually find any source sort of EVM code. I think we will definitely find it here. Oh, there is the ABI. So the ABI is what stands for Application Binary Interface. So when a dApp or a web app is trying to understand a contract, it can parse the ABI, this part of the contract, in order to understand what functions it has available and what functions and the sort of relevant bytecode associated with it. So I do think that this is basically a compiled, I mean, this is really the bytecode with some extra metadata in there, which Truffle also keeps to know maybe what its address is, if it's deployed on the blockchain, etc., etc. So we could try and deploy this thing. I think that will run the migration, so maybe we don't want to do that. Truffle, how would we deploy this? Let's just see what the deploys alias for migrate. Okay, so it does want to run the migrations to deploy contracts. Okay, so maybe we have to create a migration. That is annoying. I don't think that we have to, but we can. So, okay, well, let's just do this. This is what Truffle wants us to do. So let's create a second migration. I think we just create a file, and let's call this like deploy hello world or something. I'm just going to copy and paste what that looks like, and we're just going to be naughty here and just change the words of things to make it work. Deploy hello world. Does that look right? Oh, this is not a .sol, sorry, that is a .js. And that looks okay. Yeah. All right. So let's go. Truffle migrate. Let's see what happens. Don't expect this to work because I think this is going to try and deploy to the Ethereum public network, and I don't think I've connected to it yet. Okay, good. Yeah. So it's like something went wrong. It's trying to connect to the network and some local host thing. Check that. It's not happy. Blah, blah, blah. And this is what you're going to find inside the Truffle config. So let's have a quick look through the Truffle config. It's a module.export, so it's just regular JavaScript. And that's actually quite nice. It means we can also write scripts to help build this thing. So there's a networks thing. Okay, it's not filled in. I don't know what this is, DB thing, some compiler specification, that's fine. Good, useful for testing. Okay, so here's a local one, useful for testing. That's all good. So for now, I'm going to run an Ethereum node. So what I would do is go to Alchemy or go to Infura, one of those things, log into this thing and create an Ethereum node. All right, I've logged into Alchemy. I already actually have an Alchemy environment, but I'm going to create a new one. So we go create app. We'll call this Web3 Tech, some description. Now here's interesting. So we can choose on Alchemy what kind of environment it's the development environment, what chain it is, it's the Ethereum chain, but then also which network in Ethereum we're going to use. So we're not going to want to use real Ethereum for this demo. So I'm going to choose the Rinkeby network. So Rinkeby is a development network on the Ethereum blockchain. So it's a side-by-side chain. It looks exactly the same as the main network, except it runs on kind of like testnet ether, and meaning that I can get hold of testnet ether without burning real dollars. So I'm going to create that environment. If I come into it, I think somewhere I can get the connection credentials for this thing. Oh, view key, maybe it's that. View key. Yeah, there we go. Cool. So there's the address of my network. So now, hopefully, I'm going to just steal one of these examples here. I see this cool example here, and that one looks good. So I'm going to use that, take the comments out, call this Rinkeby, and my provider is going to be this guy. Is that one? The network ID 3, I don't think is right. The network ID for Rinkeby is network ID, let's just Google it. The Rinkeby network chain ID is 4, so that needs to be 4. Gas, this kind of stuff is, I don't think, important for now, but let's do that. So in Truffle, we've created a new network. We called it Rinkeby. We could have called it whatever we wanted, and it'll connect to Alchemy there. So let's see if we can do now a migrate. And I think I passed the network over here. So I say, oh yes, please migrate, but use the network called Rinkeby in your config. And this should hopefully now connect to the Infura one. HD wallet provider is not defined. Okay, so I think we need to import it. Yeah, there we go. Up here, because this is regular old JavaScript, we need that thing. Oh, here's our, that's an interesting thing. We'll just keep that out for now. We'll come back to that. And let's import the provider. Can't find it. Okay, so that means we have to install it. npm install. Maybe we want to save it. Doesn't really matter. So because it's npm, it's kind of easy to install stuff. So the interesting thing about this piece of code here is when Truffle runs, it almost behaves like MetaMask, right? It runs as a full-on wallet. And so which wallet does it use? So which account does it use when it interacts with the blockchain in order to deploy contracts and stuff like that? Because obviously that's to provide gas. And it doesn't talk through MetaMask, so it behaves a lot like MetaMask. And so with this, it's a nice way to provide your mnemonic to Truffle in order to do deployment stuff. But we'll get to that now. Let's just see it happen. Okay, it actually wants mnemonic. Where is that defined? Must be in here. Oh, okay. So when we provide the wallet provider, we need to actually give it the mnemonic. Okay, so we need to do this. So let's uncomment it. We remember we kept our mnemonic in this file here, mnemonic.txt. So read file sync, and I'm going to go // mnemonic.txt. Let's actually even just print it because that'll be cool. Console.log mnemonic is mnemonic And now, so each time it loads that, it's going to print out a mnemonic. Cool, so that worked. All right, looks like we're getting a bit further. So it seems like it's connected, but keep in mind that we don't have any money or any ether in that wallet. So we can't actually pay for the deployment of these contracts. So it's like the balance is zero way. So way is like cents in ether terms. And it says insufficient funds for gas and price and value. So and that is true. So if we go and look at this wallet, which is now the same one as that because we provided the same mnemonic, so they're the same wallet, we can see we've got zero. So how do we go and get some cash into that account? How do we get some ether into that account? Um, the best thing to look for is the Rinkeby faucet, and I don't think the main one works anymore, but this chain.link one does. If we go to this guy, we can say to him, this is obviously provided by Chainlink, um, and it can just give you some ether on the test network because it's really valueless, right? So if I copy that account number and I say, yes, I'd like it in Rinkeby, thank you. I don't want any link, but zero point 0.1 test ETH would be great. I'm not a robot. Click send request. This will submit a transaction and hopefully give me some money. And you don't need very much, but and now we're waiting for the Ethereum blockchain to. Okay, so my camera died. I've switched to this one, but eventually our transaction did complete, so we can see in the faucet request was completed, and we can actually click through on that transaction hash. We can actually see the confirmation on the Ethereum blockchain itself. So you can actually see status success, and there's been 2 block confirmations thus far. So as the blocks continue to go, we'll see more and more confirmations. In our MetaMask, oh, we don't see the balance there. Okay, so what we haven't done is we haven't switched. Remember, we issued ourselves a zero point 0.1 testnet ETH to the Rinkeby network, but MetaMask is still looking at mainnet. So we want to be able to switch to test network. I think you click the show hide test networks, that takes you into settings. And somewhere in here, there is a way to enable those. I show test networks, so turn that on. Go back and close this. And now when you drop down, you can switch to the test network. So we want to switch to the Rinkeby test network. Ah, cool. All right, so then we can see in that account, we've got 0.1 ETH. I think if we look at activity, we may see it. If we switch to account 2, we've got naught. But account 1 is 0.1 ETH. Great. So we funded the account. So now, if we try and do our migrate on this side, we're hopefully now doing it with a funded account. Because remembering, they're sharing the same mnemonic. So let's see what happens. All right, so keep in mind that this migrations thing happens first. So you can see deploying migrations. That was the first migration, initial one initial migration, which does seem to deploy some contract, which we don't really understand yet. We'll just ignore it. That seems to have worked. It's now pausing for 2 confirmations. That is probably a truffle config. Confirmations there. Number of confirmations to wait between deployments. I would say on test we should make that 0, but we'll wait for it anyway. I think the default is 0. So we've had 1 confirmation, so 1 block has moved. Or about 10 seconds per block is the sort of approximate. And now the migration is moving on to the next step. And then we're moving on to our next deployment. Now deploying Hello World. So this transaction hash is the hash of what was submitted to the mempool. So we should actually be able to go and look that up. If we search for it, we will find our mempool transaction. And you can see that I think that this spinning thing here means that it's not yet accepted into the blockchain yet. Well, this seems to say that it might have been. Don't know. So if we refresh it, maybe we'll see it. It could be that ring B, that this Explorer is slightly behind. I see it's saying indexing, so it could be. But according to Truffle, it has been deployed to the blockchain, and we actually have a contract address even. So there's the address of the contract. The account that was used was this 38F. That should match the MetaMask account that I'm using, 38F, yeah. Cool. All right, great. So actually, what we managed to do is we've deployed a contract into the testnet. Probably if I refresh this, we'll see it. It's still indexing. So Explorer seems to be a little bit delayed. Okay, there we go. Success. 2 block confirmation. Fine. Um, we so okay, so we've got a contract literally sitting at an address. Through the Explorer, I can even see that. I can see this contract BF7D is created. Let's click it and see what we can see. There was a fee associated with it. There was a block. You can go click. You can actually see the bytecode. Here's the bytecode itself of the contract. Interestingly, Explorer, this Ringby etherscan.io doesn't understand the contract, so it hasn't seen the source code of it. So all it can see is the bytecode, and we know that we can't really easily disassemble bytecode back to source code. So all it can really show us is the bytecode. There is it looks like it could attempt to decompile it. I wonder what that would do. I don't know. Let's try it. Online EVM disassembler. I don't know whether that will work. But it's probably going to be as bad as what you would expect to come out of a decompiler or disassembler. I'm not even going to bother. But there is a way to provide Etherscan with the actual contract ABI, like the interface to this bytecode, and then it would display the actual functions available to it, the read and write. But Truffle can do this too. So if we go Truffle, I think it's called Truffle console. Yeah, run a console with contract abstraction and commands available. This is pretty cool. So we can go Truffle console, which will always specify what network we're using or which config we're using. So this is the way you switch between development and production. And now you've got like a sort of semi-JavaScript console. I think the way we can now load our contract, so we should probably try and keep track of that contract address, that one. Where should I keep it? I'm going to make a new file or something. I'll make a readme new file. Readme only. And we'll say deployed hello world at that address. So we know that we wanted to get to our instance of our hello world object. We know that it's on the blockchain at that address. That's worth keeping that. So let's try and load it. And this is very much kind of JavaScript. So I can go let hello world equals, and in the context of this Truffle console are my contracts. So I can go hello world, and to load it from a particular address, actually I should say await here. I'll go .at, give it that address. I think this should work. All right, so this is telling Truffle, hey, go load the contract that you know about called Hello World at that address. Give me back an object called Hello World and await that. So this is like a promise. It goes and reads it off the blockchain. And now I can go Hello World, like what is this thing? And it's like, oh, it's like some kind of object. It's got an address that's pretty cool. I can see what it is. We kind of knew that. I think I'm going to got methods on it. Got methods like that, yeah. And that shows me, hey, I know about a greet method and a set what method, set what string. That's awesome. So I can even go hello world dot greet on it, call it, and it actually like returns my value. Can I go set what on it? Let's try it. Hello world dot set what to moon. I should say hello moon. And I think I would have to await this because it's a call. So this should submit a transaction to the blockchain. See what happens. And we await it. So that's cool. It seems to have worked. It's actually come back with like a transaction hash, that one. We can actually search for that transaction hash on the Explorer, see what it looks like. It goes, yes, still indexing it, so we can't view it yet, but we can assume that it's worked. And if we greet now, we're now reading the next block, which is Hello Moon. Brilliant. All right, so let's go and have a look at Explorer now. We can now see that that transaction is now reflecting. Interestingly, we should be able to call our same contract, not necessarily from Truffle, but we should be able to call it from the Explorer as well. So let's try it. I just click on the actual contract itself. So we can see now all the transactions that have occurred against this contract. And remember that BF7 is the same as that one, which is like our Hello World object. So these are the things that have happened on our Hello World object. In the past, we can see that it was created at a certain time, and who created it? It was me, 38F. It was my wallet, created it with that transaction hash in that particular block 16 minutes ago. And then we also had a change that something happened here. Remember, we called set what, and so that would have been that transaction there. It's not all that clear what has actually happened in here, but you can see that it came from the same person, it came from me as well, and happened in that block 11 minutes ago. Cool. So let's see if we can actually get this thing to read our contract. Now, I don't remember exactly how to do this. Are you the contract creator? Verify and publish your contract source code today. Yes, let's do that. Okay, there's a contract address, compiler type. Oh, do we have Solidity single file? Yeah, okay. Select the compiler version. It was that one. Open source license, no license. Continue. Let's see if we can submit our contract. So it looks like it actually just wants our source code. And you can do this through an API as well. That is obviously better than this. Enter the code below. The constructor arguments, there were none. Misc settings, I don't know. I'm not a robot. I'm not. Where are the bridges? There's a bridge. Bridge. Any other bridges? That's a bridge. Don't see any other bridges. Yeah, let's see what happens. Verify and publish. You can obviously do this through an API as well, and Truffle itself can do it. So you can set up a key to etherscan.io that Truffle can interact with and automatically upload your contract source code or expose the ABI so that you can view your contracts in the Explorer as well, which is quite cool actually. Okay, it successfully created it. So if I now go back to our contract, let's just find our contract again. There it is. Oh, a little tick now, showing that there's a verified contract against it. There it is. Yeah, okay, so I can read the code, but I could also read. So remember, there's the difference between reading the contract and writing to the contract. So now you get these new little tabs. There's a read contract view, which shows you the methods which read from it. So there's only one, it's the greet method. And if we expand it, it's like hello moon. That's all it is. Then and of course, then there's the write contract methods, which are the ones which can write to the blockchain. So there's only one method, set what. And it's like, oh, we could actually call this. So let's try it. Let's go hello Earth, Moon, Sea, Sun. I'll click right. It wants us to connect our Web3 provider, of course. So there's a button connect to Web3. If we click that, it says, well, which wallet are you using? Using MetaMask. Up pops MetaMask saying, hey, rinkb.ethscan.io would like to access your account. We go, yeah, that makes sense. So we connect MetaMask. Now, if we click right, this thing breaks. I think actually this doesn't work on Chrome. All right, it doesn't work on Chrome. I'm just going to ignore it. We don't care. And we're going to build now an app. So let's build our own front end to this contract in our own dApp. So how do we do that? What we could do is let's get back into our console and let's just see that this contract does actually update properly. So if we do our thing again, let hello world equals await hello world dot app address. Let's just modify it here. hello world dot greet. We should actually always kind of await these things, but greet we know is just a read. Set what to hello sun. We send it in there. We should then be able to read this change over here. So once that, I think I'll probably have to refresh this. Contract read, call greet. It's now hello sun. So check, it's like pretty cool. We've got one side reading, we've got MetaMask reading the state of the blockchain, we've got Truffle writing to the blockchain. So that all kind of makes sense. To build a web app, I suppose I could get all advanced and build like a React or a Vue or whatever, but like let's just go with very standard. Let's just write like pure JavaScript, HTML. So I'm going to paste probably just a basic HTML template in here and come back. Okay, I've quickly put together a very simple web application. Really, it's just an HTML file and a JavaScript file. I'm using and I'm using something called Parcel to serve it up, which is a really cool tool. You just really point it at your HTML file, Parcel index.html. It kind of reads this and it sort of pulls in and imports any of the dependencies underneath. Very basic. I've chosen not to use like a web framework like a React or Angular or Vue or whatever. I just want to keep things like really simple and just give you a really simple demonstration of how Web3 works. Of course, you should, if you're building a real app, to use like a proper framework probably. I'm just trying to keep it quite clean and simple. So I press refresh here. I can see I've created an HTML file which has got like two buttons, a read button, a write button. It's got a greeting div with different IDs. And then I'm importing the CDN distribution of Web3. I think this is the latest version. I think that's the one to use. This is probably a bit naughty. I should probably pull this into my parcel somehow, but I'm not doing that. I'm just pulling it off the CDN. So, and then I'm importing my app.js as a module, which means I can run that. And if I do, I can see my log. So that's cool. That's sort of working. So the first thing I want to do is I probably want to connect my MetaMask to my web app. So if I have a look here, I can see at the moment it's not connected. And so that's kind of the first step is, I think the method is called Web3 request accounts is the first method to look for. And okay, yeah, so probably we should actually construct it. Is that correct? New Web3. Yes, I think that looks right. So let's actually construct this thing. We're going to construct the Web3 interface. Web3.givenProvider. GivenProvider would be injected by MetaMask. So I don't want like a fallback. I'm just going to say it has to be MetaMask. Let's just try that. If we go console.log Web3, do we get something there? Let's have a look. And yes, it looks like we do get something. So there's an object provided. So it looks like Web3 constructed, okay? That's cool. The first method I would like to call is request accounts. Yeah, this guy. This one I think is pretty much the first one you should call. This method will request or enable the accounts from the current environment. So it's effectively talking to MetaMask to say, hello MetaMask, please can I request accounts from you? And it'll kind of go through like a permissions type of thing. Let's have a look at it. Yeah, so you can see it's kind of like a promise type thing. So let's do that. We're going to go request accounts. Then we'll get some sort of result. And let's just console.log that result, something like that. So if we refresh that, and already like up pops MetaMask. I'm actually in that tab, but MetaMask popped up to say connect with MetaMask. Your app on that thing wants to request accounts. Which accounts do you want to link? I want to link that account. That makes sense. Click connect. Yeah, and then what you'll see comes back as a result is really an array of the connected accounts. There's always actually one account. It's always an array, but it's always an array with one element. I'm not sure why that is, but that's just always been the case. So that's cool. So that MetaMask now for our app is now saying it's connected, which is super cool. And I can choose to disconnect it, but if I refresh it now, It won't pop up again because it's already connected. I can choose to click connect and say, hey, disconnect it. And then if I refresh and call it again, up pops MetaMask again to request access. So that's cool. That's kind of the workflow. And it should actually be on a click button, but I'm just doing it right in the beginning. As my script loads, I request the account. So I think that's okay. The next thing we're going to want to do is we want to be able to load, so we want to be able to read that Hello Moon method off of our contract. So this gets a bit more complicated. And I need to hook an event onto this button. Now, how do we do that? Is a document.get element by ID read button dot on click equals some function. I think that makes sense. Console.log read button clicked. Just test if that works. Read, yeah, okay, so the read button is clicking, that's good. I think the next thing we want to do is we actually need to instantiate a contract. So I'm going into the contract method now. And this is how we construct it, so that makes sense. So now we're going to like construct our hello world contract, but from a particular address. We're going to like load that instance off of the blockchain, and this is what it looks like. So we can go const, you know, this is the hello world instance equals that, and now we have to provide really two things. I'm not going to provide any options. So I'm going to kill that thing. We have to provide the JSON interface and an address. Okay, so we know the address. Let's just keep it here. We'll go const contract address equals something, and we'll grab it out of our README. It was that guy. So we now know the contract's address, so we can specify that there, which is that second comma. But now the JSON interface is, what the hell is that? So remembering when we built our contract and outputted this big JSON file up here, this thing actually is, this thing inside it, the ABI portion, is the contract interface, the ABI, the application binary interface. I think it stands for that. That's what we have to provide that as an object into here. So luckily with Parcel, we can import that file. So we can go, how do we do it? We go import, I think, import contract interface from /contract build contracts hello world.json. So we're going to import that JSON file, contract interface, and we're going to pass it here as the .abi. And I'm hoping that that just works. That would be amazing if it does. Okay, if we click the read button, so it could be working. And then let's go console.log hello world here. When we click the read button, yeah, okay, so it looks like it is working. To expand it, do we see that methods method? Yes, we do. And in there, we can see greet and set what. So that's awesome. We've got like now an instance of our of our contract. So now it's pretty simple. We can just call it right console.log, and let's just go hello world.greet. Let's just call the method. Click read. Oh, greet is not a function. Hello world.greet. Can we just call this actually? I don't think we can. I think we have to go, yeah, methods.myMethod.call. So there's a difference between call and send. Keeping in mind, remember we've got a read method and a write method. I think .call is the read method. So this will call a constant method, an executed smart contract method, without sending any transaction. So that does not alter the state, and send does alter the state. So I think we have to go .methods. The name of the method .call. And we should probably await that. So const result equals, yeah, let's go await. Not a huge fan of await, but let's do it. And then we write the result. Let's go read. this has to be async. Yeah, this is why I don't love. Wait, so I'm gonna use good old promises result, and then I'm gonna constantly result. I know await probably will make this look less cheaty. Methods.greet.call is not a function. That sucks. So let's just debug it. Sources, can we debug it? Also root. This is quite handy. Go there. Click it again. We've got methods dot greet. Oh, okay. It looks like maybe we have to go like that. Take our breakpoint out. Read it. Ah, there we go. Yes. Okay, so that's us calling our method. We went greet.call. Cool. So I think what we wanted to do, let's just fix this quickly, is we had this div here, nothing ready yet. We just put the hello sun into there. So when we click this, we get hello sun. We put it in that boxy there. So how do we do that? I think we go document.get element by ID. We call it greeting dot text content equals result. I think that should do it. We click read. We get hello sun there. Yay. Okay. So the next thing we're going to do, so reading from the blockchain is pretty simple. You don't actually need, like MetaMask doesn't really care. You can just read state out of the blockchain. It is happening through MetaMask, but MetaMask doesn't interact with you at all. You're allowed to just, you're allowed to dot call functions because you're just reading. But now we want to hook up the write button. So when we click write, we're going to replace the word hello sun with something else. So let's just quickly wire that one up. I'm just going to copy and paste this. Actually, yeah, we can steal that whole thing because we're going to need the contract again. Is that right? Oh, sorry, no bracket there. Okay, so except it's the right button. Oh, that's got a capital B. Let's make it lowercase. Right button. Save that. Save that. Okay. So now we are going to want to call the set greet. What was it? Something like that. Hello world dot methods dot. Actually, we'll see. We should actually see them here, right? There was dot greet and did we not see them here? I didn't actually read it. Let's have a look at our contract. It was called set what with a value. So we want to go set what. I think actually we pass the parameters up here. Hello Saturn, and then instead of dot call, I think we go dot send because now we're creating we're no longer reading. It's not a constant method. We're calling the send method, which will send a transaction to the smart contract and execute its method. Note this can alter the smart contract state. Yes. So let's look at the signature. It's like the method and then the method's parameters dot send, and then send itself has got other parameters. And I think the important one is the from address, that the address of transaction should be sent from. It does look, I don't think this is optional. I think you have to provide the from account there. So it's like who will pay for this transaction's gas. So you do have to provide this. So we have to go from, and then it's like, well, who? And we sort of knew earlier that when we did the request accounts, we got the accounts over here, and it was the first element. So if we do that, that might be the solution. Then this thing will give us back some kind of result, and let's just print it. And normally what it gives you back is the transaction, the submitted transaction. But let's see what happens if we click write. Okay, cool. So we click write and up popped MetaMask to say, hey, you're about to spend cash. Are you okay with doing this? And then MetaMask tries to give you some info. I wish this was more interesting. At the moment, it just says contract interaction. Wouldn't it be nice if it said you are calling the set what function with this parameter or something? I suppose you could maybe pull that out of here, data. Okay, so look, there's something interesting here. It's like you're passing a new what with a string, hello Saturn. You can see the hex of like what the bytecode, what the compiled EVM looks like. So that function actually is being compiled into like an EVM type of thing. And then you can even specify your gas. So I think I could have specified the gas here, but what MetaMask is doing is it's kind of calculating your gas. It probably doesn't know if this was mainnet, it would suggest an amount of gas based on the current load of the network, but it might be that this unknown is because we're on the ring bean test network, it might not know how fast that network is. I don't know, but let's confirm it. So we'll confirm it. You'll see we haven't had our then hasn't yet fired, and let's see what happens. But I suspect our then will fire only once the transaction is actually confirmed. Yeah, there we go. So you actually did see it here. It said pending in MetaMask. And then as soon as it was like committed into one block, we get the send firing. And so what it came back with is like, yes, it was, here's the transaction confirmation effectively. So this is searchable like we did on the Explorer again. And we can see some information. We can also see how much gas was actually consumed at the end of the day, the cumulative gas used. There's the actual gas used or whatever, etc., etc. There's a whole bunch of stuff going on there. So I think we called the set what function. So if we go read now, yeah, we're now reading the new value. So that is us interacting with a contract. If I click write again, up will pop MetaMask. I get to do that again. I think I can edit my gas fees. Yeah. So it is telling me stuff. It's saying the network is busy. There is a fee. Edit the suggested fee. Because remember, I can specify my own gas fee. So I can say, actually, I would like to pay a lot more because I want it to happen very quickly. So I can specify a higher priority, like a higher amount of gas that is earnable by the miner, which would then put me at the higher part of the mempool, which means that hopefully it would um, that interaction would happen quicker. It does look like I can speed it up even, so I could even adjust the gas fee while a transaction is submitted. So that's quite interesting. I can affect an existing transaction in the mempool. I can apply more gas to it if it looks like it's taking too long. That's quite cool. So that's that dynamic aspect to transactions. Okay, and there again we see the contract interaction again. There, and if we go and search for that particular transaction, can't find it, maybe too quick. Did we have our thing open? So here is our contract. Yeah, if we look at transactions, these things should have updated. Yeah, we should see, like if we go and look at our Hello World contract, we can see all the interactions with it over time, and we can see what accounts they came from, etc. That's yeah, so that is that. That is Web3 in a nutshell, the Hello World example of it, at least. Cool, thanks guys. Thanks for sticking it out this long. Hopefully that was useful. Hopefully that gave you a sort of whirlwind tour around what is Web3 all about, as well as giving you some real tangible example of like how you might start to use some of the low level pieces or how to start thinking about architecting an app. Of course, things like smart contracts can be much more powerful than a hello world setting and reading a value, but you can then start to see that you can start to build that logic of what your app does inside the smart contract itself. You can also start to define who is allowed to call various functions on that object. So you can have an object with all of its methods on it. Some of them are maybe callable by certain people. Some of them are callable by other groups of people, or potentially someone has to provide some proof of a token before they can call another function, etc., etc. All of that is sort of slightly more advanced usage of smart contracts. But I wanted to, for just today, give you a taste of what Web3 is all about and give you just an overview of like what you would do to get going with it. And from there, you can start to play and look at other contracts and kind of understand the context of where they come from. If you guys have got any questions, you know how to get hold of me. Please do. And let me know what you guys think and what might be interesting beyond this to cover. I mean, we've got options of looking at other blockchains. Cardano is quite interesting and very different. Near is again very interesting, very different. Actually, a great developer experience and a very different model. But fundamentally, it kind of works the same way, etc. So, guys, thanks very much and cheers.